Okay. So today we are going to discuss a new topic, circuits. So in this chapter, my dear, before I start this lecture, I would like to tell you something about your Physics 1 chapters with Physics 2. In Physics 1, I think you already covered chapter 22 in the last semester regarding the, not 22, 12, regarding the free body diagram. So we gave some information, and based on that you have to draw the free body diagram, and from the free body diagram you have to frame the equation for getting the answer. Am I right? Am I right or not?
Yes, yes, sir.
Yes, sir. Like that, in Physics 2, this chapter number 27, regarding the electric circuits, we gave the information in the question. Sometimes the diagram will be given, and you have to frame the equation. You have to apply the Kirchhoff's voltage rule. When you apply the rule, you have to first frame the equation for getting the answer. So especially this equation, uh, I think there will be no particular formulas. The only thing, after you read the questions, if the diagram will be given, you have to frame the equation from the diagram. And suppose if the diagram is not given, you have to draw the diagram. Clear? But the most important thing in this chapter, there is no formula. The only thing, you are going to frame the equation for getting the answer. So how you can get? You have to understand the concept. So today you are going to study two important rule: Kirchhoff's voltage rule, Kirchhoff's current rule, or we have to say junction rule or loop rule. So because the current rule has the another name as junction rule, and the voltage rule has the another name as loop rule. So today we are going to study these two rules very, and after you understand, then only you can apply the rule. I have some example question, and when I just explain that concept, please listen this class very carefully. So let's we just read what are the contents today we are going to discuss. In the content, first of all, we are going to study what is EMF, electromotive force, and we are going to get some small information about the ideal and the real EMF devices. Ideal means imagination, real means in the current day, current life. So what's the comparison between the ideal and the real EMF devices? And then we are going to study these two important rules. It's very, very important. Kirchhoff's loop rule, or called as voltage rule, and Kirchhoff's junction rule is called as current rule. So by applying these two rules, you have to frame the equation. So while you frame the equation, you should be very, very careful. Suppose if you made any mistake, especially in the signs, positive sign and the negative signs, that's matter. If you made any mistakes while you frame the equation, then your entire answer will be wrong. So please, my dear, while I just explain the concept of this loop rule and the current rule, please listen my class very carefully. And after that, by applying these two rules, suppose if you have multi-loop circuit, I have one example. And if you have multi-loop circuits, so how you have to apply these two rules. And finally, we have to complete our chapter 27 by studying the concept of charging and discharging the capacitor. So here also you are going to get some equation, and you will get some questions in the final exam also, because we are going to solve one model today after we complete the lecture. And here, these resistors in parallel and series, we are not taking any numerical question from this topic. So this topic is not covered for today, because our class time is just 1 hour. So in this 1 hour, I can't finish all these entire 8 topics. So this resistors in series and parallel is not included. So for sure, you will not get any questions in your final theory exam. So don't worry about this resistors in series and parallel. Let's we start with introduction. Introduction about the cell or battery, because in our current day, we are in our current day-to-day life, we are using this battery cell for some many applications. So we are going to get some information. My dear, listen carefully. If you have the battery, there are two important things. One is electrodes, and second one is electrolyte. What is electrodes? The electrodes is nothing but it is a conductor through which the current passes. That means you have the positive terminal and the negative terminal. That is called as electrodes in the battery. I'm talking about only the battery. And here, the internal view of this, some voltaic battery cells here. So here, inside the battery, what are the things we have? Generally, if you are open the battery, if you just break the battery inside, you can see some colloidal gel will be there. And that gel is nothing but gel-like structure. It's like a watery substance, and but it is not entirely watery substance. It is just a colloidal state. So we have two important parts in the battery. The first one is the positive terminal and the negative terminal, which is nothing but the conductor, and through which the current will passes. And the second important thing, inside the battery, you will get some electrolytic solution, and that electrolytic solution is nothing but it's a presence of free ions, which it makes electrically conductive. So inside, when you just break the battery, you can find some black color material, and that material is called as electrolyte, and it is nothing but it has full and full of free ions, and which is nothing but electrically conductive. So these two important things we are just using in the battery, because without these two things we cannot able to design a battery cell. So these two are very, very important. Now, if you want to get some idea about electromotive force of the cell, what is this electromotive force? Because the word force is given here, actually it is not a force. Actually, what's the definition for the electromotive force? Here I just gave the explanation. What is given here? It is the potential difference between the two electrodes of the cell. For example, you can see when you just take the battery, outside the battery you have the positive terminal and the negative terminal. So in between this, what is the potential? Suppose if you are not connecting, and I just clearly given in the second part, you can see when the cell is not connected in the closed circuit, that means no current in the cell. Because when you connected the cell with some wire, then only the current will be flowing because of the electrolyte. So before you connecting this battery with the closed circuits, what should be the potential that battery will have? That is nothing but the electromotive force. So this cell has two types of resistance. One is external resistance, and second one is internal resistance. The external resistance, what we are going to connect it externally. That means when you take a battery, connected one end of the battery to one resistors, and take the another battery, another end of the terminal to another end of the resistors, this R, capital R, indicates the external resistance. But when you connected any external circuit, internally there will be some resistance will be generated. That resistance is nothing but internal resistance. So that is represented with the letter small r. So what is given here? Resistance by electrolyte. That means inside you have some electrolytic solution. So when you connected the battery with the external circuit, when the current is flowing through the circuit, what will happen inside the battery? That means what will happen inside the electrolytic solution, inside the electrolytic, inside the battery, there will be some resistance will be generated by the electrolyte, and that resistance is called as internal resistance, and it should be indicated with the letter small r. So external resistance always we have to use capital R, and internal resistance always we have to use small r. And then what should be the difference between the real devices and the ideal devices? My dear, if you just take the ideal devices, you can see the two graphs. From the graph itself, you will get some clear picture. So when you plot the graph between the EMF, generally, my dear, EMF should be indicated with the letter, with a symbol, this one. So when you just plot the graph between the voltage and the current, your voltage will not be dropped. So that means in the real cases, it will not possible. So whenever you are using the real EMF devices, there will be some small voltage drop. So that's the difference. So generally, when you take the real, there will be for sure some voltage drop, because in chapter 20, we studied the concept of second law of thermodynamics, no 100% efficiency. Am I right? So we can just use this here also. Whenever you take a battery, for sure some voltage drop will be there. Whenever you connected the battery with any cell, there will be some voltage drop. So without any voltage drops, that is not possible to have that type of EMF devices in our day-to-day life. So whatever the devices we are using in our day-to-day life will have some voltage drop. So that information is nothing but the difference between the real devices and the ideal devices. Now, when you come for the voltage role and the current role, my dear, listen carefully. This topic is very, very important, because we are going to solve some question in this topic by using this rule. So please listen the topic very carefully. So today we are going to discuss these two rules, voltage rule or current rule. My dear, voltage rule is called as loop rule, and then current rule is called as junction rule. What is that? Junction, Junction. So in your theory question, sometimes we may give some different way. Define junction rule. So junction rule is nothing but the current rule, and loop rule is nothing but voltage rule. So these two rules are very, very important for designing the equation by seeing the picture. So you have to see the picture, and suppose if the diagram will be given, and you have to apply this rule very carefully. I will tell you the procedure how to apply this rule. So let's we start with the current rule, because the current rule is very easy, and we already studied this current rule in the previous chapters. And you can just see here, we have 5 branches. Am I right? That means we have 5 branches here, and in these 5 branches there are some currents. You can see I have current I1, I2, I3, I4, I5, and here you can see all these branches are meeting in this junction. Now, all these I1, I2, I3, I4, and I5 are the current. My dear, you have to see the direction of the current. So likewise, when you just have any circuit diagram, first of all, you have to identify the direction of the current. For example, if you just see this diagram, we have 5 branches. In these 5 branches, there are some currents I1, I2, I3, I4, and I5. And the most important thing, first of all, you have to identify how many current is entering and how many currents are leaving. For example, you have to see this diagram. Our current I1 and current I4 are entering the junction. And how many currents are leaving the junction? Our I2 current, I3 current, and I5 current are leaving. That's it. So when you identified how many currents are entering and how many currents are leaving from the junction, then it will be easy to frame the equation. So how we have to write? Let's read what is our definition. At the junction, which junction? This is our junction. At the junction, the sum of the currents entering the junction must be equal to the sum of the current leaving the junction. So let's we just frame the equation. How many currents are entering? I1 and I4 are entering. So you have to add these two. So because the word is given as sum of the current. So you have to add these two. These two currents are entering the junction. And how many currents are leaving the junction? And you have to take the sum. So 3 currents are leaving from the junction. One is I2, second one is I3, and third one is I5. So I have to frame the equation. I1 and I4 are entering. So I have to take the sum, and I2, I3, and I5 are leaving the junction. So which is very equal. So my left hand side of the equation must be equal to the right hand side of the equation. That's it. Because generally the junction rule will be very easy, but the most important thing is the loop rule. Identifying the junction rule is very easy, but when you are applying the voltage rule, you should be very careful. First of all, I have to give the definition for the voltage rule. What is given in the voltage rule? My dear, read this line very carefully. In a closed loop, that's the most important thing. Consider this diagram. Consider this diagram. And here I have a battery, and this battery have some EMF. And here I connected 3 resistors. One is R1, R2, and R3. And when you connected this battery with this resistor, the current will be flowing through this circuit. And here we have to consider the conventional current. What we studied in the
Doctor,
last class? Yes.
what's this symbol that have the red arrow?
My dear, it's just EMF. You have to do like this. Sometimes the students they will write E. Actually, it is not E. Just make like a epsilon symbol. Okay.
Like okay, like epsilon.
Okay. This is called as EMF. Actually, we have to write like this. You have to write like this. This is our EMF. Clear? But my
Yes.
dear, just understand the concept. Here, EMF is nothing but the voltage. Okay, because we have to use our DC circuit. Clear? EMF should be indicated with the letter epsilon. It's like epsilon like symbol which indicate the EMF of the battery. Clear? Okay, let's we come for our
Okay.
topic. So here we have the circuit. We have 3 resistors. When you connect the battery, what will happen? The current will be flowing through this. My dear, you have to see the circuit. It is completely closed. That's what in the center of the circuit, I just put some circle symbol. What's the meaning for the circle? The circle indicates the circuit is completely closed. So if you want to apply this loop rule, the most important thing, the circuit should be closed. If the circuit is open, then the loop rule will not be applicable. So for example, if you consider this diagram, I have a battery, I have 3 resistors, and all these are connected, and it is completely closed loop. Am I right? Whenever the circuit is the closed loop, you have to apply the loop rule very carefully. Let's we read the definition, and then I will tell you what you have to do. Let's we read what is given here. The algebraic sum of the EMF. My dear, what is EMF? Here, it is nothing but the battery. How many batteries you have in this circuit? We have only one battery. So in some circuits, you have 2 batteries. So when you just have the multi-loop circuit, by the time when you apply the loop rule, you have to do very carefully. And we have some questions about that. Inshallah, when we solve that question, I will explain very clearly. So for this picture, we have only one battery, and we have to take the algebraic sum. So when you have to take the sum, when you have 1 or 2 or 3 batteries, then only you have to take the algebraic sum. Suppose if you have only one battery, just separate your battery separately. The algebraic sum of the battery, which is exactly equal to the algebraic sum of product of resistance and its current. For example, you have to see here, what is this, my dear? It's a product of the current and the resistors. And what is this here? Product of current and its resistors. What is here? The product of current and its resistors. So you have to separate the battery, as well as you have to separate the product of current and its resistance. Let's we apply the rule. So here we have only one battery. So I just write this EMF one side, which is exactly equal to the algebraic sum of the product of current and its resistance. So let's we apply the product here. What is the product here? I multiply by R1 algebraic sum, and here we have another resistors. I multiply by R2, and then we have third resistors plus I multiply by R3. So that's it. So you have to separate the battery one side, and you have to separate the product of current and its resistance one side. When you separate these things perfectly, then your equation will be very. Yes, my dear, ask your question.
Doctor, I can take the current as a common factor, or will be different?
Yes, you can take. Yes, you can take. If the current will be the same, you can take as a common factor, no issue. But in some circuit diagram, the current will be different. Like when you apply the junction rule, I gave one example. When you understand that, when you just understand that concept, then everything will be easy. But in this picture, the current is common. If you want to take the current as common, no issue.
Okay.
Clear?
So generally, sometimes can be common, same, or sometimes can be different.
Usually we will give the same current. Okay, don't worry.
Oh,
okay, we will just give the same current. But when here after a few slides, we will get the multi-loop circuit, and in that multi-loop circuit, I have different currents. Okay, but you must know both these things. When you have the common currents, no problem. But when you have the different currents, you have to identify the current very carefully. Clear, my dear? So you have to see this equation. This is nothing but our voltage rule, because we separate the EMF of the battery and we separate the product of the current and its resistance. So in this circuit diagram, we have three resistors, and all these three resistors, the current is flowing. So I have to take the voltage. Clear? What is the formula? Because this is nothing but voltage. Am I right? Am I right or not? EMF is nothing but voltage. What is this? This is also voltage. Am I right? Because Ohm's law. What is Ohm's law? V is equal to IR. Am I right? Am I right or not?
Yes.
Am I right or
Yes.
not?
Yes.
So what is the voltage drop in this part? What is the voltage drop in this part? What is the voltage drop in this part? That's it. That means we are just separating the EMF with the product of current and resistance is nothing but the voltage. The most important thing, once you separate the battery EMF and the product of current and its resistance, then solving the question will be very easy. And here we have two questions, because we reduce the number of problems to three numbers. So out of these three questions, two questions are related with the loop rule. So by the time you will get a clear idea. Clear? Clear, my dear? Clear?
Doctor, here, doctor,
Yes.
we have two rules for the loop rule.
But here, what is the
What's the
loop?
difference
My
here?
dear, my dear, listen carefully. Here, just let's we see this diagram. Here,
Yes.
how many currents are here?
Three currents.
Not three currents. All three currents. All three currents are common. Am I right?
Yes. One.
So you cannot be able to apply the junction rule here. Am I right?
Yes.
Is there any junction here?
No, doctor. No, doctor.
No. But
I mean here, doctor, in the corner, right down corner, we have two
right
formulas here.
This one?
Down.
This
Yes.
one?
Yes.
My dear, both equations are exactly the same.
Okay.
I'm just moving the equation, and I just make the equation to 0. Apart from that, this equation and this equations are exactly the same.
Same. Okay, doctor.
Clear? I just move the equation. I make the equation to 0. That's it. Okay. Let's we come for our, my dear. Now you will get a clear idea. I gave one picture here, which is nothing but the multi-loop circuit. And now I need the answer from your side, because the same circuit diagram is given here. My dear, I will teach you. Please listen these things very carefully. And in this diagram, we have two batteries. Am I right? Battery 1 and battery 2. Am I right?
Yes, doctor.
Okay. Now listen carefully. And here I gave the name in the junction. What are the names? A, D, C, and B. And here we connected two batteries. That's what I mentioned. EMF of the first battery, EMF of the second battery. And here I have three resistors, R1, R2, and R3. And in R1, the current is I1. In R3, the current is I3. In R2, the current is I2. That means here the currents are different. Am I right? Am I right or not?
Yes.
It's not the same current.
Yes.
But listen carefully. You have some junction here. You have some junction here also. You have some junction here also. Am I right? Am I right or not?
Yes.
So now, if you want to apply the junction rule, first of all, you must see only the current, because when you write the junction rule, you no need to worry about the battery. Only you have to consider the current. Listen carefully. In R1, the current is in the downward direction. Am I right? Am I right or not?
Yes.
Am I right?
Yes.
Okay. This current is coming here. Am I right? The I1 is coming here. Am I right? Okay, I3 is coming here. That means these two currents are meeting this junction. Am I right? Which junction?
Yes, yes.
The junction here is D. Am I right?
D.
Okay, which current is leaving from the junction?
No one.
This one,
I2.
I2 is
Oh,
leaving
no,
from the junction.
I
So
try
how
to.
you
Yes,
have
yes,
to
yes.
write the how you can write the equation? My I1 plus I3, which is exactly equal to I2,
I2,
because two
I2.
currents
Yes,
are
yes.
entering the junction and one current is leaving the junction. That's it. When you apply the junction rule, you no need to worry about the battery EMF, because when you apply the loop rule, then only you have to consider the EMF of the
Doctor,
battery.
this is for junction D only, right?
Yes, whenever you have
You
the
are
junction, then
considering.
only the current rule. Whenever you have the junction, then only the current rule will be applicable. Clear?
Yeah, I mean this equation you just made. This just only for junction D. It will
Yes,
be different in
that's.
junction C and A, right?
Let's we see. Okay, let's we see the junction C. Okay, let's we just see this junction C. How many currents are entering here?
And C
When
I1.
you see the
The
vector,
junction,
I2. I'm sorry.
I2.
I2.
I3, I2 are entering, and which one is leaving?
Yes. I1.
Okay, that's it. For every junction, it will be different. But here I just focus only on junction D. By that we got this equation. Clear?
Okay.
Clear?
Yes, yes, doctor.
Okay. Now let's we come for of the load, because current rule is very easy. But the most important thing, you must learn how to apply the voltage rule. So for that, what I am going to do, just a minute. I just keep one more. I just first of all I will erase this.
Doctor, loop rule is the voltage rule. Okay.
Voltage rule, correct.
Okay.
Okay. Okay, my dear, listen carefully. First of all, here, how many loops you have? Because when you apply the loop rule, you must need the closed circuit. Am I right? I gave the name A, B, C, and D. The most important thing, first of all, you have to identify the name. How many loops you have here, my dear? Shall I tell you one by one? This is your first loop. Am I right?
Yes,
Right.
2 loops.
That means A, D, B, and A.
AD.
What is our first loop? A, B, D, and A. Am I right?
Yes.
Okay. What is your
AD.
second loop? Both are same. ADBA or ABDA. Both are correct. Am I right? Am I right or not?
Yes, yes, doctor.
Better. I can just write in your own way.
A, B, D, or A.
Okay. A, D, B, A. Both are correct. Clear. So this is my first loop. What is my second loop? A. What is my second loop, my dear? My second loop is B, D,
C,
C,
B, D,
and B. Am I
C.
right? B, D, C, B. Am I right?
Yes, yes, doctor. B, C,
Okay.
B.
What is my third loop? The third loop is the entire loop. Am I right?
Right.
What is
Yes,
our
yes,
third
doctor.
loop? Just give me the name. B. Okay. Let's we start from here. A, D, C, B, and A. Am I right? Am I right? Am I right or not?
Right.
Yes.
A,
Okay.
B,
Now,
C.
see
Yes,
A,
yes, yes.
D, C, B, and A. So
A,
for
yes.
each loop, you can frame the equation. Am I right? Am I right or not? Am I
Right.
right?
Yes, yes, doctor.
Okay.
Right.
Okay. Listen. Okay. First of all, because the space is very short, I can just use it again. Okay. Let's we consider our first loop. What is our first loop? My first loop is A, D, B, and A. Let's we frame the equation for this. My dear, here you can see the direction of the current will be given here, because the main current given by the battery is in this direction. Let's we start from here. You have to separate the battery EMF and you have to separate the current with its with its resistance. So let's we separate. What is our EMF? This is our EMF, which is exactly equal to, my dear, this is the direction of the current given by the battery, and here the current I1 is also in the same direction. Am I right? Am I right or not?
Yes.
Yes, doctor.
So
Right.
that means this has the positive value. My I1 R1 has the positive value, and come here, come here. And now your battery current is here, but your I3 is opposite. So what should be the sign? Positive or negative?
Minus. Negative.
Minus
Minus.
I3 and R3. That's it. if you want to make the equation in terms of equal to 0, my EMF minus I1 R1 plus I3 R3, which is exactly equal to 0.
Doctor, can you please repeat it again?
First, we separate the battery EMF. Am I right?
Yes.
Okay. In this loop, how many resistors you have? You have two resistors, R1 and R3. Am I right?
R2, R3, yes.
Okay. And in R1, current I1 is flowing. In R3, current I3 is flowing. Am I right?
Okay, yes, doctor.
Okay. Now see, this is the red color sign is given. That means the main current is from the battery is going like this. Clear? Clear?
From I1.
So you have to compare the remaining current with this red color arrow. Let's see. This red color arrow in this direction, and my I1 is also in the same direction of the red color. Am I right?
Yes, same there.
So it has positive value. Okay, let's become for I3. My red color current will be coming in this direction, but my I3 is in the opposite direction. Am I right?
Opposite direction, yes.
So what should be the sign you have to put?
Minus,
That's it. We are just putting negative here. Clear?
Yes, clear.
Okay, let's we practice for the second. I did the answer from your side. Let's we consider this loop. Second loop circuit, B, D, C, and B. First of all, I have to write what is my EMF. What is my EMF, my dear? E2. I separate the battery, and let's we consider, because the battery current is given here, so you have to compare the rest of the current with this red color arrow. My dear, the battery current in this direction, but my I2 current is opposite direction. So what should be the sign for this?
Minus.
Very good. Minus I2 R2, and let's we see this. My I3 direction and the red color direction is opposite. Am I right?
Am I right? I3 with the same. I3 with the
yes, doctor.
EMF.
My dear, how the I3 current
minus
will be
same direction?
No, different. Right.
Yeah. So what should be the sign? Minus I3 R3. Now, if you frame the equation equal to 0, I have to make this to this side. So what will happen, my dear? Minus I2 R2 minus I3 R3 minus EMF 2, which is exactly equal to 0. Am I right? Am I right?
Right.
Yes. We will get the same equation here. See?
Or we can't take it with plus in the
no side. Problem. Okay, no problem. Let's we just move the I1 and R to the left hand side. My dear, listen carefully. Just move this to the left hand side. What will happen? Both will be the same. Plus I2 R2 plus I3 R3 also the same. Because when you just multiply with this minus, then you will get this equation. Am I right?
Yes, doctor. Same.
Both are exactly correct, because in mathematics, if you multiply with the same sign, then you can remove all the signs, because negative and negative get positive. Clear?
Yes, clear.
Okay, let's we come for, my dear, the third is very, very important. You have to complete. You have to consider this loop rule for the complete thing. So now I need the answer from your side. Better I can just include one more slide, and by that we will get a clear idea. New slide.
Doctor, right now we have 2 EMF. How it will be?
That's what I'm coming, my dear. That's what I'm just going to make a new slide, and now I need the answer from your side. Clear?
Sure.
Okay. Okay. Now I have to consider the entire circuit. Which circuit, my dear? Let's we start with A, D, C, B, and A. Okay, my dear, here you have two batteries. Am I right? We don't know which battery is the strongest one. Am I right? Am I right or not? Because each battery has different range. But in the circuit diagram, they did not mention any value for the battery. Let's we consider our E1 is stronger one. Clear? Let's we consider. Because out of these two batteries, we never put the same value of the battery. Two batteries will have the different values. Clear? So for example, I consider my E1 is the strongest battery. And you have to see, my E1 current will be red side, left hand side, but my E2 current will be in the right hand side. Am I right? Am I right or not?
Yes.
Okay. In this case, first of all, you have to see the strength of the battery. Which battery has the maximum value? Sometimes one battery is 5-volt battery, and the second battery will be 10-volt battery. Which one is the strongest?
10.
10 is the strongest. So you have to consider the circuit diagram like this. For example, here I consider my E1 is the strongest. So I have to consider the direction of the current from the battery will be here like this. Clear?
From the strongest.
from the strongest. Always you have to consider the direction of the flow of the current from the strongest battery. I consider my E1 is the strongest, so I consider the direction of the current like this. Clear? Clear, my dear?
Okay.
Okay,
Yes.
now you have to separate the battery. So my EMF of the battery is the strongest. Which one is the weakest? Which one is the weakest?
EMF2.
Because my arrow is opposite to this arrow. Am I right? So what should be the sign?
Minus.
Negative. Clear? Which is exactly equal to the product of the current and its resistance. My dear, listen carefully. This is my arrow of the current, and my I1 is also in the same direction. So what should be the sign? Positive or negative?
Plus.
Very good. I1 R1, and my current is coming here, and my direction of the current from the battery and then I2 current is in the same direction.
Also,
so what should be the sign? Plus I2 R2. That's it. Clear? Clear, my dear?
That's doctor.
That's it. So if you want to equate this equation to 0, E1 minus E2, that means EMF1 minus EMF2, when you just move this to the left hand side, minus I1 R1 minus I2 R2, which is exactly equal to 0. Clear? And that equation is given here. Clear? Clear, my dear?
Yes.
So in your question, suppose if the circuit has two batteries, first of all, you have to see what should be the range of the battery. For example, if your first battery is 10 volt, if your second battery is 5 volt, then you have to give the importance for the first battery, because the direction of the flow of the current from the battery, you have to consider from the strongest battery. Clear?
Clear? Yes, doctor. The strongest one.
Clear? Clear, my dear? Because
yes,
we have a couple of questions in this chapter, and you must know how to apply this rule. Understand? Clear?
Yes, doctor.
Okay.
Clear.
And then we are going to apply the same thing, my dear, because I don't want to waste the time much. I don't want to waste too much of time in this slides. First of all, you have to see the circuit diagram. Here we have two equations for capacitor charging and capacitor discharging. My dear, capacitor charging will be given by this equation, this one. What is this Q? Q is the initial charge. Sorry, Q is the final charge. Q naught is the initial charge, and here we put the symbol tau. My dear, here the tau is nothing but it's the combination of the resistors and the capacitors. It is not a relaxation time, because in the previous chapter we studied tau is the relaxation time. Am I right? My dear, for this chapter, the tau is not a relaxation time. The tau is the combination of the RC circuit. That means the resistors and the capacitor mixed, because whenever you have the circuit with the resistors and the capacitors, we have to say it's a RC circuit. Clear? Clear, my dear? Okay. Now listen carefully. This is our main equation, and I just split this equation into two cases. Suppose if you want to charge the back capacitor, what you have to do? You have to see this circuit diagram, my dear. You have to see this circuit diagram. We have the two-way switch, which is switch A and B, and we have one battery, and we connected one capacitor, and we have one resistance. Now, my dear, when you connected the battery A with S, what will happen? What will happen? The current will be flowing in this direction. Am I right? Am I right?
Yes, doctor.
Yes.
Am I right? And that circuit diagram is given here. Because the current, we have to consider the conventional current from the battery. The current is flowing. Whenever the current will be flowing in this direction, what will happen? The capacitor will store some charge, and there will be no current in this area. Am I right or not? Is there any current in this area?
No, doctor.
Nothing. Am I right? So when you make the current, when you make the switch A to S, when you connected the A with S, what will happen? Then the current from the battery will be flowing through the circuit. Now what you have to do? You have to apply the loop rule. My dear, how to apply the loop rule? You have to separate the battery, and you have to consider the current with the capacitor, because you have to apply the voltage rule here, and also you have to apply the voltage drop, because we already studied the equation. What is the capacitance equation, my dear? Capacitance, which is nothing but Q over C, Q over B. Sorry,
yes.
Q over
V.
V. Am I right? Am I right or not?
Yes.
Do you remember that?
Yes,
because in chapter number 25 we studied. So this is our voltage drop. Am I right? So capacitance, which is equal to Q over V. Therefore, V, which is equal to Q over C. Am I right? Am I right or not?
Yes.
So
yes,
see here, when you apply the loop rule, this is your voltage for the capacitor. This is your voltage for the current with the resistors. And when you apply this rule, because we already studied this equation, when you substitute this equation in the main equation, because this is our main equation, and the solution of this main equation is given here, and the answer for this equation will be given as Q, which is equal to Q naught multiplied by 1 minus e power minus t over tau. So the main thing here, we have to apply only the voltage rule here. We have to apply only the voltage rule, because whenever the circuit will be closed, then only you have to apply the loop rule. And the most important thing, the solution for this equation, which is nothing but this one. And how we got this equation? We got this equation by applying the voltage rule. In the similar way, we have to connect the switch with S. What will happen? Only the current, because the current will be flowing in this direction. Am I right? Am I right or not?
Doctor, why not in the opposite direction, right?
My dear, we have to consider this is your positive terminal, this is your negative terminal of the capacitor. Always the current, we have to consider the conventional current. Am I right?
Yes.
So that's what I just put the direction of the current like this. Even if you swap, if you just change the direction of the current, your equation will be the same. Only the things you have to multiply with the negative sign, and then finally your final equation will be the same as the previous one. Clear?
So Doctor,
Clear, my dear?
just right now we switch off the battery. There is no battery.
Yes. Now there is no battery. Whatever the charge you stored in the capacitor, this charge will be utilized by the circuit. Am I right? After some time, what will happen, my dear? Because we store some charge in the capacitor. When the charge is utilized by the circuit, how much charge will be here? Because the charge is going to discharge. Am I right? Am I right or not?
Yes.
Whatever the charge you stored, it will be going to nullifying. And here you are storing the charge in the capacitor, but here you are taking the charge from the capacitor. Am I right?
Yes.
Am I right? And when you apply the loop rule, your equation will be like this, because this is nothing but our voltage drop and across the capacitor. And then what is the current flow through these resistors, which is exactly equal to 0, because you have to apply the loop rule. And you know the formula for the current, because formula for the current, which is nothing but the charge over time. So you have to take this I, substitute here, and finally your equation will be in this form, and the solution for this equation will be given here. My dear, here I directly give the equation, but in the next slide I gave the explanation how we got, by using this voltage loop equation, how we got the main equation. All this explanation I just work out, and this is the basic integration. The basic integrations I'm just using in this. If you find the time, just to have a look. But in the exam, you no need to write this one. My dear, in exam, you no need to write this many steps. But the most important thing, these equations you have to memorize. Which equation? This equation. Clear?
Which one, Doctor? On the left? The blue one.
In the left, in the left equation, see, I put the star symbol. Am I right? So this is for charging the capacitor, and this is for discharging the capacitor. Clear? Clear, my dear? Charging the capacitor and discharging the capacitor. And the explanation here, I already wrote it in the separate paper, and this is a basic integration method. I'm just applying the basic integration method here. So whenever you find the free time, just have a look, because here we must know how we got the answer, because here I directly give the answer here. Am I right or not? In this slide, I directly give the equation and the answer for this equation. But how we get this equation from... Yes?
Yes. Continue.
Clear? So we must know where we got this answer. So that's what I just gave the proof here. Here I just work out in the separate paper, because if I explain, because generally in our type of exam, we never ask the student to write this much of steps. Only we have to consider the more importance for the numerical type question. But for the numerical type question, we need only the final equation. So for charging the capacitor, you have to memorize this equation. For discharging the capacitor, you have to memorize this equation, because in this chapter we have one question about the charging and discharging. Clear? So the most important thing, you must memorize the equation. Clear, my dear? Understand?
Doctor.
Yes.
The tau here is what exactly?
This is for charging. For example, your question will have the information for charging the capacitor, how to find the relaxation time. So how to find the tau, which is nothing but the combination of the R and C. Clear?
So, Doctor, tau here time?
Or... No, it's a time. It's a time calculation, time constant. We have to say it's a time constant.
Okay, time constant.
Time constant. It's not a time. It's a time constant. Clear?
Yes, Doctor.
Clear, my
dear?
So
the unit here, Doctor. It's what?
Yes,
second
time constant is nothing but the second. The answer should be in terms of seconds.
Okay.
Clear? And here, my dear, you have to see this diagram. For charging the capacitor, how your capacitor will be charged? Your charge will be slowly, and after it reaches the maximum, it will be saturated. Am I right? Am I right or not?
Mm-hmm.
And after you make the connection like this, your stored charge will be utilized by the circuit,
Discharge.
and whatever the charge you store here, it will be
Decrease.
decrease. Clear? Clear, my dear?
Yes, Doctor.
Clear? So please memorize this equation. This equation is for charging, this equation is for discharging, and here this C and R is nothing but your time constant. Clear?
Tau. Mm.
Clear? Clear, my dear? Okay. Now, this parallel resistors in parallel and series not is included in your chapter. So please, my dear, we reduce the number of problems. So we discarded this resistors in parallel and series. So no need to worry about the formula. You will not get any question from this topic. Clear? Clear, my dear? Clear?
Doctor.
Okay. We just recall the equation.
Clear, Doctor.
What is the equation? What is the equation for charging? Charging the capacitor. Charging the capacitor, charge which is equal to the initial charge multiplied by 1 minus e power minus t over tau. Am I right? And for the
T over
discharging,
tau.
q which is equal to q naught e power minus t over tau. Clear?
Mm-hmm.
Clear, my dear? Because these are the two equations we are going to use for solving the question, especially for charging and discharging. Okay, we are going to solve three. Yes.
And the questions will be clearly mentioned, charge or discharge.
Yes, it will be clearly given. We just solve first question. By the time you will get a clear idea. My dear, here we are going to solve three questions, and out of these three questions, your first question is related with charging or discharging. Clear? And the rest of the two questions are related with the loop rule. Understand?
Loops. Mm-hmm.
Okay. We start with the first question. What is given in the first question? Better I can just make the question a little bit top. By that I can write something here. And I have to make some space also.
Doctor, chapter 28 also will be on loops or?
Chapter 28, it's related with the magnetism.
Okay.
Because till that, I think we are going to study the concept of the current. But when you come to chapter number 28, it is related with the magnetism. Clear?
Magnetism. Okay, clear.
Okay. Read the question, my dear. What you understand from this question? Listen, this question is related with charging or discharging. First, now you have to tell me whether this question is related with charging or discharging. Let's read the question. What is given in the question? What multiple of time constant? That means we are going to find the answer with the multiplication of the tau. The answer should be in the multiplication of tau. Okay. What multiple of the time constant gives the time taken by the initially uncharged capacitor in an RC series circuit to be charged to 89% of its final charge? That means, can you please tell me this is related with charging or discharging? Initially, you have the uncharged capacitor, and then you are going to charge. Am I right?
Charge. Yes.
Clear? So now you will get a clear idea. Am I right? This question is related to charging. Am I right or not?
Charging. Yes.
Because initially you take the uncharged capacitor and then you charge the capacitor to how many percentage?
89.
89% we are going to charge that uncharged capacitor. So initially I take the capacitor which has no charge, and what I'm going to do, I'm going to connect that capacitor with the RC circuit, and now I'm going to charge that capacitor. So that means we are going to play with which equation? Charging equation. So what is that equation? Q which is equal to Q naught 1 minus e power minus t over tau. Am I right? Am I right or not?
Yes, Doctor, right.
Okay. What is the initial charge you have in this battery? What is the initial charge, my dear? The initial charge we have in the capacitor is Q naught. Am I right? Am I right?
Yes, Q naught.
Okay. What is our final charge? Our final charge should be charged to 89% of initial charge. Am I right or not? Am I right or not? 85% from the initial charge. Am I right or not?
Yes.
Okay. We play with the equation. What is our equation? I'm going to write this equation. Q which is equal to Q naught multiplied by 1 minus e power minus t over tau. Now what I am going to do, what is our final charge, my dear? Our final charge is nothing but 89% of the initial charge. Am I right? Am I right or not?
Yes, right.
Yes.
So in this place, what I'm going to do, I'm going to write, because this Q represent what charge we are going to save. So that means my Q is nothing but 89% of initial charge. So in this place, I'm going to write this as 89% of Q naught, which is exactly equal to Q naught multiplied by 1 minus e power minus t over tau. Am I right? Am I right or not? Clear?
Yes.
Okay, you can cancel this Q naught and Q naught, because left hand side and right hand side we have the same charge, so I can cancel. How you can write this 89%? You can write this 89%, 89 divided by 100. Am I right? Am I right?
Yes,
Yes.
Which is exactly equal to 1 minus e power minus t over tau. Now, what I'm going to do, I'm going to keep this term here, and then I'm going to move this term to the left hand side, right hand side. So when I just move this term to the right hand side, this becomes negative. When I just move this term to the left hand side, this becomes positive. Am I right?
Positive. Yes.
So how I can write e power minus t over tau, which is exactly equal to 1 minus 89 divided by 100. Am I right? Am I right or not?
Yes.
Now you know how to take the LCM. When you take the LCM, so this becomes 100. So 100 minus 89 in left hand side e power minus t over tau. Am I right? Clear? Clear? So
Yes, clear.
100 minus 89, which is exactly equal to 11. Am I right?
11.
Am I right or not? So 11 divided by 100, which is exactly equal to 0.11. Am I right? So
Right.
minus e t power tau, which is exactly equal to 0.11. Am I right? Clear? Now what I'm going to do, because we are going to find the time in terms of time constant, so I have to
Clearly,
avoid this
doctor.
exponential. So what I'm going to do, I'm going to take natural log on both sides. Natural log on both sides. So what will happen, my dear? When you take the natural log, and when you take exponential of minus t over tau, and right hand side natural log of 0.11. My dear, whenever you take the natural log for the exponential term, what will happen? This exponential will gone. Am I right?
Cancel, yes.
So what is left? Minus t over tau, it's left. Am I right? Am I right or not?
Yes, right.
And right hand side, you have natural log of 0.11. Could you please tell me what is the answer for natural log of minus 0.11?
Minus 2.21.
Minus 2.21 you got, and left hand side we got minus t over tau. My dear, listen carefully. This negative get cancelled with this negative. So how much time constant you will get? Therefore, t, which is equal to 2.21 times of time constant. So this much time constant is needed to charge 89% for this capacitor. Am I right? Am I right or not?
Yes, doctor.
Right.
Clear? Because they need the answer in terms of the multiple of the time constant. So that means what number
So,
is needed for multiplying with the time tau. Clear?
doctor, I have a question, doctor. Why you said the 89% of the Q charge here?
My dear, the initial charge. My dear,
Like,
initially you have the capacitor. There is no charge. Am I right?
yes,
Am I right?
zero charge.
Okay, that means I take my initial charge in this capacitor is Q naught. Clear?
Clear.
Clear? And after you charge, how much charge is stored in this capacitor, my dear? You have positive charge here, you have negative charge. So
Some charge
89% from the Q naught. Am I right or not?
from Q naught. Yes.
That's what I just say. Initial charge is Q naught. My final charge is nothing but 89% of the Q naught. Clear?
Yes, doctor. Now I get
Clear?
it.
Clear? So please, my dear, these type of question will be given. So you must read the question very carefully. First of all, you have to identify whether this question is related with charging or discharge. If the question is related, so the questions clearly they mention initially your capacitor has no charge. That is nothing but uncharged. And after that, you charge to 89%. So that means this question clearly tells you about charging the capacitor. Clear? Clear?
Yes, doctor. Clear.
Okay. So let's check our answer. Yes, our answer is exactly same because we take t which is equal to 2.21, but here we just rounded. So better you just write whatever the answers you get. Clear? Clear, my dear?
Clear, doctor.
Okay. Now, second question. This question is a loop rule. We already studied this, am I right? So now I need the answer from your side. My dear, first of all, please see the diagram. And first of all, you have to identify whether the diagram is closed loop. Is it closed loop or open loop?
Closed, doctor.
Closed.
Closed loop. How many batteries do you have?
2 batteries.
2 batteries, E1 and E2 you have, am I right? What is the value of E1?
2 volts.
2.
What is the value of E2?
Yes, 2 volts.
So that means
3.
which one is the strongest battery?
3. The
E2.
2 one.
That
2.
means your second battery is the strongest battery. So you have to consider the direction of the current like this. Clear? Clear?
Clear.
Understand, my dear? Understand? So
Yes,
you have to check how many batteries you have. And first of all, you have to check what are the types of battery, because whether the range of the battery, first of all, you have to identify it. So which battery is strongest, then you have to give importance for the strongest battery. So now you have to see the battery current from E2 will be in this direction, but the current from the E1 is in this direction. Am I right or not? So both are opposite to each other. So now you have to apply the voltage rule. How to apply the voltage rule, my dear? Could you please apply the voltage rule for this? It's very easy. First of all, you have to separate the battery, and we have to give the importance for the strongest battery. So here the strongest battery is E2. So I have to write E2 first. Am I right? Am I right?
2 minus E1.
Yes.
So E2 minus E1. So we separate the battery, which is exactly equal to, my dear, listen carefully. The current is flowing like this. Am I right? The current is flowing like this. That means the current is entering in the same direction of E2. That means plus I multiply by R1, because small current R1. And also the current is entering this R, capital R. That means plus I multiply by R. And also the current is entering R2 plus I multiply by R2. Am I right? Am I right? Clear?
Yes, Doctor.
Clear, my dear? Now, what we are going to find in the first question, we are going to find what should be the value of the resistance R, because R1, R2 value is already given. The small R1, R2, that means the internal resistance of the battery is given as 3 ohm. That means R1 and R2 have the same value as 3 ohm, and my EMF of the first battery is 2 volt, and my EMF of the second battery is 3 volt. And is there any value about R? We don't know. That is our first question. So first we are going to find what should be the value of the R. So I'm going to use this equation. First of all, I have to rearrange this equation. How to rearrange, my dear? So what I'm going to do, I'm going to separate the battery because we already separate. So now what I'm going to do, we take the current as the common term. So here all the current is very common. R1 plus capital R plus small r2, left hand side E2 minus E1. Am I right? Am I right or not?
Yes.
Am I right? And now we are going
Yes,
to
right.
find the value of the R. So these are all in the multiplication form. So I can take this current to the left hand side of the equation. So my equation becomes E2 minus E1 divided by current, which is exactly equal to R1 plus R plus R2. Now we are going to find the value of this R. So it's very easy. So how you can rearrange E2 minus E1 divided by current. When you move this R1 to the left hand side, this become minus, and when you move this R to the left hand side, this become minus, which is exactly equal to the resistance. Now substitute the value. We have the value for all the things. E2, which is nothing but, what's the value of E2? 3 minus 2 divided by the current is given as 1.5 milliampere. So my current value is 1.5 multiplied by 10 to the power of minus 3 minus of 3 minus of 3, because R1 and R2 will have the same value. So now you have to tell me the answer. What's the value, my dear? What's the answer?
Doctor, will be
Yes. 660.6
660.6. What's the unit?
ohm.
Ohm. So this is our answer. If you want to write in terms of power, 6.6 multiplied by 10 to the power of 2 ohm. Better you can write as it is what you get from the calculator. No need to convert in terms of power. Both answers are correct. So this is the answer for the first question. Am I right? Am I right or not?
Yes, doctor. But I have a question, doctor.
No.
The first thing,
Yes.
doctor, we should separate the battery,
Yes.
then the I. Am I right?
Yes.
Mm-hmm.
Then the current and the resistance, you have to take the product, because this current, because I told you this E2 is the strongest battery, so current will be flowing like this. Am I right? Am I
The
right?
I. Yes, yes.
So that means the current, for example, see, when the current will be coming in this direction, this current is entering R1. Am I right? Am I right?
Yes, yes.
And also
It
this
will
current
make.
is entering R. Am I right? Am I
Yes,
right or not?
yes.
And then this current is entering R2. So all these R1, R2, and R have the same positive value, because the current will be exactly in the same direction of E2. Am I right?
Mm-hmm.
Clear?
Yes, yes, doctor.
Okay. Now, what
But
is your second question? Yes.
doctor, how we know the direction of R1, the R small one? Is it
My
down
dear,
or up here?
there is no direction for the resistors. Okay, you have to consider only the
Uh-huh.
direction of the current. My dear, you have to consider
Current.
only the
Okay.
direction of the current. There is no
Mm-hmm.
direction for the resistors. Only the direction will be given only for the current.
For the current. Okay, okay.
Clear? Okay. Now, what
Clear.
is your second question? What is your second question? What is the rate? What is the meaning for the rate? They are asking about the power. Am I right? The rate. If you come across the word rate, then it refers the power. So whenever the current is flowing through this, what will happen? Thermal energy will be generated. Heat will be there. Am I right? In our house, when you just turn on any electrical devices, after some time when you touch, you will feel the heat energy because of the current flow. Am I right? Am I right? So whenever the current is flowing through the resistors, the resistor will generate some thermal energy. So that means the rate here represent the power. How many formula you have for power, my dear? In the last chapter we studied P, which is equal to IV, P, which
Three
is equal
forms.
to I square multiplied by R, P, which is equal to V square over R. Am I right?
Mm-hmm.
All these three formulas we studied. Am I right? My dear, here you please don't consider this here. This V is nothing but your EMF. Understand? So how you can write P, which is equal to I multiplied by EMF, P, which is equal to I square multiplied by R, P, which is equal to EMF square over R. Am I right? Am I right? Clear? So which
Yes, yes,
formula you
right.
are going to use here? Which formula you are going to use here? Because we have three formulas.
Second
Which
one.
formula is exactly? You can't
The
use this.
second one,
Why? What's the
doctor,
reason? Because you can't use these two. Why? What's the reason, my dear?
because we have two EMF.
We have two EMF. So you will get confused. So whenever you have two EMF, we cannot be able to predict these things. So we cannot be able to use this formula with the EMF. Only we can use this. So the answer for the second question is nothing but P, which is equal to I square multiplied by R.
By
So the
R.
current, which is all the current is given for 1.5 milliampere, which is nothing but 1.5 multiplied by 10 to the power of minus 3, and the resistors just before we find as 660.6. Am I right? And that will be your answer. And the unit will be watt. Clear?
Yes, clear.
What's the answer?
Doctor, we should use the second formula for power because we have
Because we
two
have two
EMF.
batteries. So we
We
have
have
two
two
EMF. So
batteries.
it's not possible to use, because we cannot, because we can substitute only one value of the EMF. Am I right? But here in the
Yes,
circuit
yes.
diagram, we have two batteries. So it's not possible. Clear?
Yes, yes, doctor. Clear, clear.
Okay. What's the answer here?
Three square. Yes, doctor. It will be 1.48 10 to the
Okay.
power minus 3.
Minus 3. That's it. Let's we check our answer. Yes, we exactly got 660 resistance, and then we got 1.48 multiplied by 10 to the power of minus 3 watt. So, my dear, in this way, you have to apply the rule very carefully. First of all, the circuit should be closed, and the second thing, you must identify what is your battery power. If the battery has the highest value, then you have to give the importance for the highest value of the battery, and you have to consider the direction of the current from that battery. Clear? In this question, our second battery is the very strongest one, so I consider the direction of the current from the second battery. Clear? Clear, my dear?
Yes, yes, doctor.
That's it, inshallah. I think the time is about to finish, so we have one more question, and inshallah we will solve that question tomorrow, third period. Understand? Clear?
Inshallah, doctor.
Okay, brother. Yes, my dear Mr. Yasser.
Doctor, what about the assignment?
My dear, listen, my dear, just a minute, please listen here. Yesterday I prepared the assignment, very easy, one word answer. Please try to complete your assignment in this week, because after that your Ramadan vacation will start. So I need your paper in this week, especially Thursday. If you sit for just 20 minutes, you will finish all these questions. It's not a biggest question. All the questions are one word answer. All the questions are one word answer. Directly you have to write the formula, you have to substitute the value, you have to get the answer. So I need your assignment paper in this week, especially Thursday.
Doctor,
Clear? Yes.
can I submit the assignment after Eid?
No, my dear, please try to. If you don't have any class, please give your assignment paper to your friend and please ask them to submit. Clear? Because if I just gave on Sunday, then everybody will submit on Sunday. How many chapters are included in the assignment? My dear, I included from chapter number 21 to 26. So 21, 22, 23, 24, 25, 26. There are 6 chapters I include. Each question from each chapter. Clear? There are, you can see the questions. There are 6 questions are there. Each question is from one chapter. Clear? If you take chapter number 21, one question will be there. If you take chapter number 22, one question will be there. That means there are 6 questions are there, and 2 questions are multiple choice question. It's very easy. Read the question and give the answer. Each question carries 0.25 marks. So totally, I directly give the mark for 5. Once you submit, inshallah, immediately I will grade your paper and I will enter the assignment mark in the SIS, inshallah.
Can I leave, doctor?
Doctor,
Yes, you can leave. You can leave. The time is over. Inshallah, see you tomorrow. Dr. Muhammad, I came to college. I knocked the door and no one opened. Oh, sorry, no one opened, and no one opened for me to. So I gave my experiment to my friends, and he will bring it after period 6. No problem. Ask your friend to submit on my paper table. Okay, I will collect the paper tomorrow.
Doctor,
Mr. Yazir, okay, okay. Yes, my dear.
the degree of assignment 1, it's not available.
My dear, still I did not upload the marks. Once you submit the second assignment, I will grade both and I will add it both and then I will show you both, inshallah.
Okay.
Clear? It's with
Yes.
me. I already graded. It's with me. Once you submit the second assignment, I will make a grade and then I will add together. Then I will show you, inshallah.
Okay.
Okay, brother. See you, inshallah.
Inshallah.
Assalamu alaikum.
Thank you.
Thank you so much, doctor.